everyone. Welcome to the first session of contributed presentations. I'm Hanna Wallach, and I'm going to be chairing this session. And before we get started, just a couple of housekeeping notes. There were a lot of people sort of sitting on the floor over on that side of the room. If people move towards the other side of the room, we will have more available seats. So I definitely recommend scooting over, and that will sort of make some more room for people. Second point, here's how this is going to go. Since this is the first session of contributed talks, I want to tell you how this is going to happen throughout the conference. Each of the papers will have exactly 10 minutes to present their work. I will physically remove them from the stage if necessary. I used to play competitive roller derby. I am not afraid to do this. Okay. After the presentations, we will then go into Q&A for all of the papers in that session. So there will be no questions between the individual papers. All questions will be at the end. Great. So this session is on framing and abstraction. And we have 3 papers in this session, and they're all really awesome. So they cover the choices that people make throughout the machine learning development process, starting right with problem formulation or task definition. They also cover historical lessons on measuring fairness from the standardized testing literature. And they cover abstraction as a point of failure when thinking about sociotechnical systems. And these papers are some of my absolute favorite papers at the conference, so I'm really excited for this session. And with that, I am going to hand over to our first presenter.
All right. Hello, everyone. It's a great honor to be here. My name is Samir Passi, and I'm a PhD candidate in the Department of Information Science at Cornell University. Today, I'll present the paper co-authored with Solon and Barocas titled Problem Formulation and Fairness. Let's start things off with a brief description of the larger problem that motivates our paper. In contemporary discussions of data science, the process of going from high-level goals or questions to working data science systems is often taken for granted. When formulating data science problems, however, success is never guaranteed, and the process is far from linear. High-level goals must be made into problems that data science can solve, and practitioners frequently struggle to turn amorphous goals into well-specified problems. Members of the FedStar community have identified some notable cases where a poorly chosen target variable sets a data science project down a troubling path, predictive policing being a prime example. In practice, the outcome or quality that we want to predict is not one that has been well observed or measured in the past. In such cases, practitioners look for other target variables to act as proxies. For example, substituting arrest for crime. But the implications are broader still. What problems practitioners choose to solve and why and how they choose to solve those problems has profound normative and fairness implications. Let's see this empirically. The paper builds on ethnographic fieldwork with Data Vector, a multi-billion-dollar e-commerce and new media corporation located on the US West Coast. I worked as a data scientist with Data Vector's core data science team for 6 months, while simultaneously conducting ethnographic research on corporate data science practices. In the paper, we focused on the specific project of one of Data Vector's subsidiaries, a company called CarCorp. CarCorp provides special financing services for car loans, a niche branch of financing for people who either have low or bad credit scores or a limited credit history. The company collects data on people requiring special financing for cars with the hope of generating leads for car dealers looking for potential customers. In this project, CarCorp's high-level goal was to improve the quality of the lead data. Improving lead quality could help ensure that existing clients do not churn, that they continue to give their business to CarCorp. Early discussions between the business and data science teams revolved around 2 key questions. What is lead quality, and how do we measure it? Now, different business team members had different ideas about lead quality. Some argued that a high-quality lead was a lead with a high salary. Others believed that the lead was good if the dealer had the lead's desired car in their inventory. Now, although there were differences, everyone agreed on one thing. A good lead provided business to the dealer. A good lead was an actionable lead. The lead quality problem was narrowed down to a simple question. How likely is someone to secure special financing when you send them to a dealer? Quality was equated with financeability. A good lead was a financeable lead. The company recognized, however, the lead financeability was really a function of dealers' decision. Now, different dealers had different special financing approval processes and requirements. A lead financeable for one dealer can be, for various reasons, unfinanceable for another. financeability had to be defined and measured in relation to specific dealers. Financeability, in fact, meant dealer-specific financeability. With this definition of lead quality, the data science problem became a matching task, matching leads to dealers that were most likely to finance them. Thus, dealer decisions became a proxy for dealer-specific financeability, the data on leads financed in the past by dealers. The data science team was instructed to work with CarCorp's data engineers to get access to historical lead data sets. Upon investigating relevant data sources, however, data scientists declared that there wasn't enough data on which leads had or had not been financed in the past. I won't go into details, but the short story is that the company had not been able to create sufficient incentives for car dealers to provide up-to-date approval feedback. Now, the project could have stopped here, but it didn't. Further discussions ensued between the two teams to see if there was still a way forward. Was there a way to predict dealer-specific financeability using the data that happened to be already available? Could something act as a proxy for dealer decisions? A viable alternative appeared in the form of credit scores. The higher a lead's credit score, the more likely they are to secure special financing. The company had access to leads' credit score data in two ways: data from affiliates to whom leads self-reported their credit scores, and data bought from third-party lending agencies. For legal and practical reasons, however, CarCorp only had access to credit data in the form of credit score ranges, and this data was available for about 10% of the leads. The teams wondered if it was possible to infer credit score ranges for the remaining 90% of the leads using the available 10%. If possible, credit score ranges could act as a proxy for dealer decisions. A financeable lead would be a lead with a high credit score. There was, however, a practical challenge. Different affiliates placed the same credit score in different ranges. It was not possible to simply use the credit score ranges as class labels for training, as the ranges overlapped. They needed to be reconciled. As data scientists worked on the problem, however, the business team came up with an easier solution. The analysts believed that having a credit score higher than 500 greatly increased a lead's likelihood to secure special financing. And this piece of information had a significant impact on the project. Only two credit score ranges were now important. Don't reconcile them, just label them as above or below 500. A financeable lead was a lead with a credit score above 500. The matching problem had now become a classification task. The credit score threshold of 500 was a new proxy. Now, this solution, well, it proved less helpful than expected because certain credit score ranges traversed a crucial threshold. As a result, leads could not be cleanly separated into the above and below 500 ranges. Data scientists tried many ways to overcome this challenge, but things just weren't working out. The project continued for a few weeks before it was halted when it seemed impossible to reliably infer whether leads were above or below the threshold. The teams considered purchasing additional credit score information from third parties, but ultimately rejected the idea due to its uncertain utility and significant cost. Let's stop here now and take a look at one of the many concrete takeaways from this case study. We find that the normative implications of data science systems evolve alongside changes in the different problem formulations of lead quality. On the one hand, the proxy of dealer decisions. In this matching task, the goal is to recommend leads that match the preferences expressed in dealers' previous decisions. Here, financeability operates on a spectrum, a more or less attribute. Each lead has at least a chance of seeing the light of day, of being sent to at least one dealer with the highest probability of financing it. On the other hand, the proxy of the credit score threshold. In this classification task, the goal is to separate the above 500 leads from the below 500 leads. Here, financeability operates as a binary variable, yes or no. Only leads with scores higher than 500 are sent to dealers. Consequently, leads in the below 500 category will never see the light of day because the company believes they're of low quality. Now, there's no reason to believe that these two problem formulations are going to have the same normative implications. But which one of these do we prefer from a fairness perspective? Now, the matching version seems more fair if our normative priority is to maximize a person's lending opportunities. If, however, our normative priority is to mitigate existing biases in dealers' current lending practices, then the matching version is no good, as it has the potential to amplify existing biases. In this case, the classification version is normatively preferable because it potentially encourages dealers to consider leads different from those that they have financed in the past. Now, it's far from obvious which of these two concerns is more serious, and hence which choice is normatively preferable. But it's clear that different problem formulations pose different risks. Target variables and proxies help equate goals with data, but also serve to frame the problem in subtly different ways, raising different normative concerns as a result. We describe this and other concrete takeaways in much greater detail in the paper, in which we argue that problem formulation is an important site for empirical and normative investigation. If normative implications such as unfairness flow in part from the very formulation of the problem, then we need to understand why and how data science problems are formulated the way they are, and why formulations that seem normatively preferable do not prevail in practice. We recognize that translations are always partial, often driven by practical and organizational constraints rather than explicit normative considerations. Our goal with this research is to make a case for studying the consequences of different translations and of the everyday practical judgments that drive them. In doing so, we open up the work of problem formulation as an important site for research and for intervention, an upstream site for downstream changes. Thank you.
This is joint work with Margaret Mitchell. My name is Ben Hutchinson, and a year ago I had a problem. I was new to the field of fairness in machine learning, and I was keen to read the seminal papers in the field, and I wanted to trace the origins of the ideas in the field back to their roots. And as I did, I started to question this cartoon history of fairness in machine learning, and I started to delve back prior to 2011. When I did, I realized that these quantitative definitions of fairness that had arisen in the field of standardized testing in the 1960s and 1970s mirrored those that had been independently discovered in machine learning in the 2010s. And perhaps this is actually not so surprising, because there is this deep structural correspondence between standardized tests and machine learning models. So for a test, we have a set of questions. For that set of questions, we collect responses, and those responses are scored. We then sum the scores to produce an aggregate score, possibly a weighted sum. That sum might then be normalized to fit some distribution. And based on that final score, we then make predictions or decisions. So as I looked into the origins of these quantitative definitions of fairness, I started to think of this golden age of the 1960s and 70s, and then the 2010s as this renaissance or rediscovery of these quantitative definitions. And with tongue very firmly in cheek, we might think of the period in between as a winter of fairness research. There are, of course, differences between the fields. And in the 1960s, the primary concerns of the fairness researchers that I looked at were to do with education and employment. Arguably, some of the highest profile concerns in the 2010s have been concerns around sentencing, policing, and surveillance. So as I looked into this, I was keen to understand more the motivations of the researchers of this period. Why did this research happen at this particular time in history by these particular people? And thankfully, some of these people are still alive, and I tracked down some of them, and I met and spoke with Marshall Jones, who was once called the most dangerous man in American academic life because of his role in the civil rights movement in the 1960s. And as I chatted with Marshall and his wife Beverly, who's an equally remarkable and important figure, she was very influential in the women's liberation movement in the 1970s, I really realized and appreciated how important the civil rights movement of the 1960s had been as a motivating factor for this research. And of course, the Civil Rights Act of 1964 was also critically important. Specifically, it outlawed discrimination on the basis of race, color, religion, sex, or national origin, specifically mentioning the domains of education and employment. And so we see that immediately after the passing of the Act, researchers of the period are discussing what the implications of this new law is for the field of standardized testing. What are the implications for people developing standardized tests, and the implications for people using standardized tests to make decisions in employment and in education? And we see discussion about an awareness of the fact that tests contain cultural assumptions and the impossibility of removing cultural influences from tests. Anastasi wrote that maybe the best we can hope for is tests that presuppose experiences that are common to cultures. And nevertheless, we see this optimism as well of the period, such as by Robert Guion, who believed that if we could develop fair tests, we could break down barriers to economic opportunity, and so the memory of discrimination, he believed, would be wiped out. And so in the paper, we catalog this whole set of quantitative definitions of fairness that arose in the 1960s and 1970s, and we link them to their relatives in the machine learning fairness literature. We see relationships to what is now called sufficiency, separation, independence, as well as other contemporary criteria. In some cases, the relationships are equivalences. In some cases, they're relaxations or generalizations. There's far too much here for me to go through today, but I do want to briefly mention a couple of these. There's this very important early work by Tian Cleary in 1966, and she viewed fairness as a prediction problem. She was concerned with fairness of SAT scores and other educational testing, and she was concerned with how well did the test predict a student's future performance. And she thought a test was unfair for a group if it tended to underpredict that group's performance. So here, for example, if we take a given level on the y-axis, which is the target variable we're trying to predict, we see that for that level, we get lower test scores for the black group than for the white group. By 1971, there were already multiple competing definitions of fairness. However, they'd been expressed in different ways, and one of the contributions of Richard Darlington was to express or reformulate some of the existing definitions by that time in a common language, and he uses the language of correlations to compare them. And we can see here that 3 of the 4 definitions that he's considering actually have close relationships to ideas of separation, sufficiency, and independence. That is, various independence relationships between the variables of race, test score, and the target variable. He also has this rather, I think, clever method of graphing the fairness criterion, and he uses this graph to demonstrate that the criterion are only compatible under very special conditions, such as the test being a perfect predictor of the target variable. We also see researchers concerned with the fairness of the decisions made using tests. And we see various different definitions of what types of decision rates should be compared. One of these is looking at equal true positive rates. This was Nancy Cole in 1973. And this same Nancy Cole in 2001 had this to say: "The spurt of research on fairness issues that began in the late 1960s had results that were ultimately disappointing. Research over the last 30 years or so has not supplied any analyses to indicate fairness or unfairness." So one of the questions we discuss in the paper is how can machine learning try to learn from these similarities and these ultimate disappointments to avoid a similar fate. And 4 high-level lessons that we try to take away from this are staying relevant to the law and to public opinion, and to maintain connections to human values and to real-world decisions. We also try to point out some research opportunities which we think, looking at the history of testing, suggests. One of these is, rather than looking at like Platonic ideals of fairness, instead digging deeper into the possible causes and consequences of different flavors of unfairness. In particular, one method that's been used in the testing literature is digging into the unfairness of specific test questions, which in our case we can be looking at specific input variables, and they use an approach called differential item functioning to do this. We outlined a few other research opportunities as well, including are correlations useful diagnostics of unfairness in practical real-world scenarios? Correlations are, of course, different from independence, although in practice they're not always that different as diagnostics. We think often because some of the tests that are used to make education and employment prediction results are often not very predictive of people's future performance, that looking at decision-making in these low prediction scenarios, low accuracy prediction scenarios, is an interesting area of further research. We have a kind of a variation of calibration that flips the variables y and r around that we motivate by a gap in the literature, and a few more research opportunities, and thank you. For more details, the recording of our tutorial yesterday, I think, will be available. Thank you.
Every good talk should start with a joke. Well, it's an academic conference, so maybe a different joke. And this is basically the story of how this paper came to be, with two computer scientists, two sociologists, and a lawyer walking into a conference room. And what did we talk about? Well, the first thing we talked about was abstraction. Abstraction is possibly the most fundamental concept in computer science. It's something you learn on day one of your first programming class. The idea of abstraction is to take a problem, remove all the irrelevant bits, and find the shiny core. Solve the problem, the shiny core problem, and then apply it everywhere, applying the wrapping as you need to in different places. Abstraction is an aesthetic. It's a value. It sort of ingrains everything. We think about what's good and what's elegant. We use words like an elegant abstraction, a nice abstraction, a clean abstraction. And the contention of this paper is that abstraction, this core value in computer science, is also a key obstacle when we have to deploy algorithms of the kinds we talk about in sociotechnical systems. And what we argue in this paper is that there is a series of traps that appear when we apply these concepts of abstraction and we try to solve sociotechnical problems, and that we need to understand these traps, where they come from, and then hopefully by recognizing them and naming them, another thing that's very important in computer science, naming problems, we can actually hope to mitigate some of these questions. So without further ado, let me get into the traps. The first trap is the framing trap, and it's a failure to model the entire system over which a social criterion like fairness will be enforced, and we've heard some of that earlier in the keynote today. A simple example is, you want to build a fair risk assessment tool, you're worried about bias. You spend a lot of time optimizing the different notions of fairness and making sure you get the classifier to do the right thing. But then you don't realize that the judge who's looking at your recommendation might actually ignore the recommendation. And so even though your part of the system has worked, the entire system is still not working because you failed to model that. The portability trap, another trap that sort of is core to the idea of abstraction, is the failure to understand that when you take a solution, your nice shiny problem that you solved, and take off its wrapper, get the solution, and apply it somewhere else, the assumption is that you can just merely put the wrapping back on and everything will work fine. And it actually may not. And the failure to recognize that as a portability trap. The formalism trap gets a little more tricky. It's a failure to account for the way in which social concepts like fairness, like discrimination, like bias, seem to resist mathematization or formalization of the kinds. We spend a lot of time talking about different definitions of fairness and how to formalize them. But the fact that these notions can often be procedural, contestable, which means different stakeholders have different views of them, and contextual, means that the definition has to be dynamic and changing and cannot be fixed in place, which a formal definition desires to do. The ripple effect trap is a trap that comes from failing to recognize that once you take your formalism and insert it into a system, that the system will actually react around it. sometimes in ways you may not expect. And again, this is something we heard about earlier at the keynote. One easy example of this is predictive policing. You build a system you think is predicting crime, and what you end up doing is building a system that predicts arrests, which is not what you want to do. The final trap is a much more philosophical and also pernicious trap, because it's a thought process trap. It's a failure to recognize that, it's not always the case that technology must be at the core of any solution. And we had a much more catchy title for this trap earlier, and we felt we should remove it, but it's really the Elon Musk trap. So the methodology we chose to adopt to think about this work is to apply principles from the field of science and technology studies to try and understand where these traps come from, how to recognize them, and how possibly to mitigate them if we can. And so the field of science and technology studies understands that when we deal with technical systems, we're dealing with socio-technical systems, and it tries to understand the way actors, social actors, interact with technology and shape it. And the hope is that by looking at past studies of past adoption of technology, we can learn something about how new adoptions might play out. I won't be able to analyze all the traps in this manner, and I encourage you to look at the paper for more details. We'll take 2 of the traps and analyze them to try and get a flavor of how we can think about these more in a more disciplined way and where solutions or at least mitigations might come from. So let's take the portability trap, which is the basic, if you recall, the idea that you could take a problem and port it over to a different domain and it'll work just the way it worked in the original domain. So to try and understand why this is a trap, we sort of make use of the theory of user scripts, which comes from the anthropologist Madeleine Akridge. Her idea was that when technology does get deployed, and it's deployed successfully, there are a number of unwritten and unspoken scripts, if you wish, other pieces of tech that work around the technology to make it actually work in a particular context. And because these are unspoken and often sort of unwritten and not written down, you're not always aware of their presence. And so when you take the idea and you transplant it over without the scripts, the ecosystem around it, things might fail. And if you ask now, well, what should we do about this? How do we bring these scripts back into explicit focus? In fact, it's kind of nice to see that there's already work in the community here. In fact, a paper that you'll see in the next session, among many others, that talk about trying to do this. For example, this paper on model cards says, take a model and build a model card, a spec sheet around it, which essentially creates a script for how it's used and under what conditions it works and doesn't work. And there's been many other nice papers in this area, data sheets for data sets, nutrition labels for rankings, and for other classification schemes. So there's quite a lot of ongoing work in this area right now, which is very encouraging to see. The next trap is that we wanted to analyze here is the formalism trap. And to understand the formalism trap, it helps to integrate ideas from SCOT, which is a social construction of technology, of methodology within STS. And what it tells us is that when you have a problem and you're trying to bring in solutions to this problem, there's a period of what is called interpretive flexibility, where many different stakeholders will bring in their solutions and try to apply them to the problem. And during this period, these solutions coexist, and over a period of time, eventually the solutions converge on one set of solutions, often driven by which stakeholders have a voice and have power in the room, and not necessarily based on which one was best or not. So this process is called closure, and often what's worse is that you get rhetorical closure, where people merely redefine a screw to be a nail because they have a hammer, and therefore have solved the problem. What we see now in the community is that we do have a fair amount of interpretive flexibility in dealing with formalizations of fairness, and so the caution we have to exhibit is trying to avoid early closure, trying to find the one true definition of fairness or unfairness, as the case may be. And realizing that even the act of formalizing itself is sort of a position that we take that may not capture all the nuances in a sort of a very broad notion like fairness or discrimination. One way to think through this, right, is to look at an example. Let's take the example of risk assessments when you're trying to predict whether someone should be released pre-trial, for example. If you work through these traps, going backwards is what we recommend, starting from solutionism, you might say, well, do we need a risk assessment tool at all? And this is a discussion that's happening in many, many jurisdictions. Should we just release people on their own recognizance, or should we even try to build a risk assessment tool? Maybe this is not the right thing, and that's an actual discussion we hear a lot of in the community. If you have got to the point where, for statutory reasons or otherwise, you do have to build a risk assessment tool, understanding the ripple effect means you kind of want to do pilot studies to see what the effect of a policy might be. You might want to state clear social goals, and you might want to have a monitoring mechanism to see how the system is working on an ongoing basis. This is something that almost never happens with these tools. They're put into place with a lot of thought, but no one ever bothers to maintain them. Avoiding the formalism trap might mean that you want to create, for one thing, interpretable models. You might want to allow challenge. You might want to understand that the model has to address not just the prosecutors and the judges, but also the defense attorneys, and also the community where these decisions are being made and what kind of impact it'll have on them. Worrying about portability might mean that you have to be careful about off-the-shelf methods. Taking a system that's been trained for Kentucky and applying it in Utah. Will it actually work when you do that? And under what conditions will it work? And the framing problem, well, at least try to include at least one human element to worry about the labels, the target labels, and the proxies, right? In the case of this, are you actually trying to build a tool for recidivism based on conviction? Are you building it based on rearrest? This became a big issue in Pennsylvania's Sentencing Commission guidelines over a few months ago. I'm not providing solutions here, but that because I don't want to indulge in solutionism. But this is a process that you can go through to try and understand and mitigate some of these traps. There's much more to say here about the process of writing this paper itself, of all the many, many arguments we had over the course of a year writing this, and the not just the jargon differences, but the fundamental epistemological disconnects that happen when computer science sort of talks to the social sciences. And that's something we can have another conversation for later. But with that, I want to thank my wonderful co-authors, Andrew Selbst, Dana Boyd, Sorelle Friedler, and Janet Vertesi, and thank you all for listening.
Okay, everyone, we have a little bit of time for questions, so I'm going to have all of the speakers come up here. We have 2 microphones, I believe. There's one over there in that aisle, and there's one over there in that aisle. And if you would like to ask a question, please line up and do so.
Hi, Arvind Narayanan from Princeton. This is a question primarily for the first speaker, but I think every paper in the session had something to do with this issue, which is that when machine learning and data science are taught today in courses, problem formulation is generally treated as someone else's problem. So how can this ethnographic field work and the insights you've talked about be translated to case studies or to the education context? Thank you.
Thank you for the question. That's a fascinating question, and one that we have been talking about, at least at Cornell, for a fair amount. How is it that we bring back what we have learned in the ethnographic context, and can we teach that as course modules to different primarily CS classes? One of the things that we have learned is just by including or changing the way we structure class projects has already helped in some ways to bring this about. Here's how a CS class project goes. You're a team of 5 computer scientists. Here's the problem. Here's the data set. Go and solve it. Here's the metric on which if you get more than 85%, hooray, you get an A+. The world doesn't work like this. We all in this room know. Just by including like, okay, you 2 are computer scientists. You 2 are business heads. And you have to convince these business heads that your product is the better one. Right? That already changes a lot of the landscape of how students come to learn how the real world operates. It's not about just having 95%. It's about making people believe in your 95%. So just by making the classroom look a little bit more like the outside, if it's artificially, we have already begun to see effects in how students learn about these practices. If you want to know more about what we have done at Cornell, please feel free to find me at some point.
Very, very quick comment. I just want to do a shout out to a blog post that Hal Daume had written many years ago, trying to identify the pipeline of debugging in machine learning, where he sort of talks about all the stages you go through from the initial goal to the actual product, and makes the point, much like Samir and Solon had done, that in machine learning we focus on steps 6 through 8 of a 15-stage pipeline. We never talk about the rest. So Google the blog post by Hal Daume on debugging ML. That's awesome. I use it to teach students all the time.
I just want to make a quick point too. Not because I work in education, I actually work for Google. And I think we have a really similar problem with software engineers and developers, and the question of how do we educate people who've already been through the education system without a training in these problem formations. And I think one of the useful things there is to get software engineers working really closely with people such as UX researchers and also privacy researchers, because these people have great skills in thinking like critically and adversarially about the effects of user harms. So.
Hi, this is a question for Ben. In your slides, you had a note from one of the researchers in the testing literature saying that there was a disconnect between the public's view and the community's view. Can you speak more about that disconnect?
So that was a comment by Nancy Cole in 2001. And in that paper, she's specifically talking about the fact that often we publish like group level statistics of like how many people from this race or this gender were admitted to college without a whole lot of context for interpreting those numbers. And so without kind of bringing the public along or staying attuned to that, the field of testing fairness kind of faced a bit of a backlash from the public. So I think the way that, I think for us in kind of fairness in machine learning, making sure we communicate our results to the public is really important.
Michael Ekstrand, Boise State University. This is a question for both Suresh and Ben. Would it be like thinking about the two papers together, would it be meaningful to think about reinventing the wheel as a sixth trap? And do you have thoughts or examples of failure cases you've seen that might have arisen from that, or ideas about purposeful things we can do as a community to try to avoid that trap?
It's definitely a trap. It's a trap we're very good at in computer science, at reinventing the wheel. I think it's because every time we reinvent the wheel, it's shinier and it sort of moves better, or something like that. But I think I actually would view this not as one of the traps we would think about, because we view those traps as failures of abstraction. I don't think, while reinventing the wheel is a big problem, it's not clear to me it's a failure of abstraction so much. It's a different kind of failure of historicity. So maybe Ben might have sort of a more useful comment on that.
Yeah, I'm not sure I have a solution, but I have personal opinions. I kind of worry that sometimes because so much of what happens, like especially currently in machine learning with amazing stuff happening with deep networks, is so amazingly new, and there's this temptation to think that everything we do is new, and not looking to the fact that so much of what's happening in machine learning is really doing things at scale that were previously done. So, but yeah, I don't really have a solution.
Cool. Michael Veal, University College London. Question probably for Suresh and Samir, and it's quite a simple one. What do you think the consequences of both of your papers are for the way that papers should be written in this community? Should there be more front-loading of these kind of questions, and how would you affect that kind of change?
Thank you, that's an amazing question. Something we have been thinking about a lot while writing our own paper. One thing I could not mention, because it's a 10-minute presentation, is that our paper is not just empirical. We draw a lot of ideas from sociology and history of science in particular, critical data studies, and a fair amount from history of data mining in particular. In STS, for instance, reflexivity is one of the most highly coveted tenets of research, right? You think about your own research, you treat yourself the same way you treat your actors. And something we have been thinking about a lot of, we can say, why did you as a data scientist ask this question in this way, and I'm going to analyze it and tell you all about what you're thinking. The fact that we are asking the kind of questions in this room today is the same thing. We have been sort of trained to see the world in a particular sense, to look at certain things as problems, the hammer and nail being a prime example of what the analogy is. The short answer is, you should always be reflexive about the kind of question you're asking, and ask yourself, why is it that this is the question that I'm interested in, or the community at this point interested in? The historical context is extremely important, something that we have seen today in one of the presentations already. Other thing to keep in mind is, and this is something that I don't mean it as a critique, but just it's a feature of every conference, that every presentation sometimes comes along and saying that, all right, so here's the right answer. And here's my right answer. To reinventing the wheel, as Suresh clearly mentioned, is sometimes not about reinventing the same thing over and over again. It's by making it a little bit more shiny, but trying to understand that everything that you do adds just one step to the entire trajectory of where the research is going, and which direction you're going to take is very important for this community, especially at this point in time.
Very quickly. I'm glad Samir mentioned reflexivity. I learned of this term exactly 24 hours ago, and I know everything about it now. But Dana Boyd mentioned this in the doctoral conversation, but I completely agree from my understanding of what reflexivity is. You have to look at what you're doing and why you're doing it. So we spent a lot of time worrying about the fact that our paper was going to send people into a defensive crouch where we basically were telling them, don't ever write any more papers because you're going to fall into these traps. And we were worried about that. We tried to attempt to give a process by which you could introspect about the work you're doing. And then one of our reviewers said, I wish you had given us a clearer flowchart to solve these traps. And as I say this, I realize I'm falling into your solutionism trap, so never mind. Thank you, whoever that reviewer was. I think it's important to be reflexive. It's important to be humble. And I think that goes back to your point as well. What I like about the papers that I've read in the community so far is that we're willing to accept that there are major limitations to what we're trying to do, and we state them up front. As John talked about, sort of being very clear about model assumptions, about what models can and cannot do. We have to be very humble, very clear that we are merely building upon what's out there, and we have to be cautious in what we claim. And hopefully the whole ecosystem of reviewing and accepting papers and writing them will encourage that kind of humility, and I think that'll help.
Okay, that is all we have time for. Before we go to break, Dana has a quick announcement, but first I want to thank all of our speakers.